Did you get your final answer?
Not yet. Hold on. Get it here.
You guys getting there? Figuring it out pretty good?
Yeah.
I think so.
Okay. It turns out, I didn't want to like spoil the math surprise, right? But it's pretty similar. This one's going to be pretty similar, including the computation to the ones that you just did. Not quite the same, but very, very close to being the same.
You know what the final answer?
The total field due to all three of them.
Yeah.
Okay. So the total. So for the third charge, as you might guess from the math, you're going to get the previous magnitude in the x direction that was in the x direction is going to be in the y direction now. And so you're going to get another z magnitude that's the same as the previous. So the total answer when you combine all three fields together should have a y component and a z component. The y component is going to be like 2158 volts per meter. And the z component will be 8632 volts per meter.
Okay.
Yeah.
And
that 8632 number, right? So is basically that comes from it comes from the 2877 times 3 is where you get the 8632. So this is the z. Does that make sense?
yeah.
Yeah.
Okay. So it turns out, that the z component is the same for all of them because they're the same distance. Oh, pardon me. The same distance from that point. Yeah.
Okay.
Okay. And then some of it's just a little tricky because you have to put in, that 1/4 pi epsilon is it gets a little tricky, mostly because that constant is really high, and so and we'll talk about the meaning of this a little bit more later, but it's the dielectric permittivity. And you may remember this from your physics classes, but you can think of this, well, we don't need to go into it too much, but you can think of this as basically a material property that describes how easy it is for things in the charges in the material to move around when they're subjected to voltage potential. So we'll talk about that some more later, but this number is a constant, and usually in air, ER equals 1. So that's why you'll just use this.
Okay.
Yeah. All right. Well, I'm gonna go to another room now. So.
Thank you.
Okay.
Yep. Hi guys, how's it going?
Good.
Good. All right. I think this is looking pretty close. Yeah. So let's see here. So yeah, in what you're gonna find is that when you do the math for E3, right, you're gonna get some numbers that you've seen before. It's just that instead of the magnitude being, you'll get the magnitude in the y direction for E3 the magnitude in the y direction for E3 is going to be the same as what you calculated as the magnitude in the x direction for the other charges. And then the z magnitude for E3 will be identical. Okay. So you'll add all of those up. I'm not quite sure. I think I just want to point out one thing. Gabriel, is this your work, Gabriel, or who's? Yeah, okay. So right now, if you're calculating E3, E3 does not include this 5754 number. So the E total will include this. But to write the E3, you want to sum this to, this is actually, yeah, it's actually the total amount. So what you've written down is not actually E3, it will be the total. But
I thought you wanted to use E3 to represent the total amount. That's why I just wrote E3.
Okay. All right. So just wanted to point that out. All right. Any questions for me? Feel good about how to do this?
Yeah.
Okay. All right. I'm going to go to next breakout room now. All right. How are you both doing? Did you get a final answer?
Yeah, or at least I did.
Yeah.
Daniel, I think multiplied by the wrong epsilon.
Yeah. So
So
yeah, we'll talk about epsilon a little bit more, but let me just make a couple notes about it. So we have epsilon, right? This is the dielectric permittivity. And we can write epsilon as a relative epsilon multiplied by the constant. And the constant, right, this and in free space, so I think this problem, what does it say? Yeah, this problem says they're in free space. So if the problem says something like in free space, that means that the relative permittivity is equal to 1. And this permittivity, we'll talk about this more, but you could think about this as being a way of thinking about how a material responds to being subjected to electric potential fields. Okay, so different materials respond differently, right? So if you think of a material, it's made up of all these atoms, all these molecules, and each one of the molecules is made of atoms. Those atoms have those protons in the core, they have electrons surrounding it. And when you subject a material to a potential field, those electrons, right, they're loosely around, they're like loosely scattered around that center. And so those electrons can move around to some degree when they're subjected to outside forces, such as created by other charges or other potential fields. And so these numbers describe how things respond inside of that field. That's where these come from. So if it says in free space, just you consider the relative permittivity to be 1 and use this constant, which is a universal constant. Any of that sound familiar? Did you talk about that in your physics class?
yeah, I remember going
Yeah.
over this. So okay, remind me again, what's that F for? What is the F? What unit is the F?
S.
F,
Oh,
sorry, F.
it's farad.
Oh, okay. Okay. That makes sense.
Yeah. And yeah, so because farad isn't that one's not what do they call it? It's not fundamental. So there are other ways, I believe, of expressing this in other units, but this is the most common way to express it.
Sweet.
Right. Okay. All right. Well, I'll leave the room and I'll bring us back together in just like another minute or so. So.
Okay.
All right. Nice to be back. So hopefully you got that. I spoke with several of you about dielectric constants. We will use that more in the future. We'll discuss it more. But for now, remember this is equal to this. And then if the problem, like this one, says in free space, then you should assume that the relative permittivity is 1. And this is always constant. (8.85 times 10 to the minus 12 farad per meter). So I'll leave the final calculation on this one up to you. But you should be able to get to that last problem. The math is going to be very similar. Your answer will be for the field on E3 is going to be very similar to what you got for E1 and E2. The last part of this problem says if you add another charge, what is the force on that charge? And so just wanted to make a quick connection between fields, charges, and force. And we can get the force on a charge is due to the E total. Okay, so this is from part B. And then this is the charge. And so if you add a new charge, so if you have a total field, E total, right, and you have some charge here, this E total will exert, let's say, some force on the charge Q. And that force can be calculated. It will be in the direction that E total pushes the force. It will be in that direction and will be based on the strength of the charge and the strength of the field. So the force will also be in this same direction, whatever direction that is. All right, that is everything that I have for you today. We'll keep working on, oh, I don't think I showed that. Did you guys were not seeing my screen, right?
Yeah.
Yeah, very sorry about that. This is what I just drew. If you have some, you'll have some force is charge multiplied by the field. So if you have some charge and you have a field, then the force will be in the same direction that the total field, the total electric field exerts at that point. So the force will be in that same direction, but it will have a different magnitude. The magnitude of the force will be based on how much charge is in that location. Okay, so we'll talk more about electrostatics next week. and I'll stick around if you have any questions, but if not, I'll see you next week.
Thank
Dr.
you.
Chrysler.
Yeah.
For
Thank you.
homework 2, I wasn't able to run the module even after installing Java on my system.
Yeah, so the modules, you need to follow those directions very closely or else it'll be very difficult to run. So for me on my MacBook, I had to like switch over to using Firefox browser. And then I also had to like whitelist the site, and all those directions were in the the website.
Yeah, for Windows, it had me install Java and then restart my system and then to use Mozilla Firefox. And I did all of that and it's
Yeah. So I think I think sounds like the other people were able to get it. If you want to give that another try today and send me the answer, like I don't know, let's say before Friday at midnight. So in the next 2 days, then
I'll try. If it doesn't work, I'll probably try going to the lab as well. I
yeah.
can do it on campus and I'll let you know.
Okay. I mean, you aren't going to lose tons of points, and if you don't do it at all, you aren't going to lose tons of points. Since you came to me and told me what was going on, I won't take off too much. I'll give you a little bit of extra time. I'll take off like, I don't know, 10% of the points on that problem. Not too much. But
I'll try. Because I want to get the experience and know as well. So I would still try to get it done, and I'll let you know.
Yeah, it's worth it too to try it because there's some of the modules later that are really helpful. That one is good, but there's some that are really helpful for visualizing things in some of the later problems. So yeah, so
I'll work on getting it.
Okay.
And I would let you know how it goes.
All right. Yeah, thanks. And if you're still having problems, let me know, set up office hour time. We can work through it together as well. So thanks for telling me, Daniel. Have a nice day.
You.
Bye.